the 1st of April 1945. A unit of American infantrymen from General George Patton's Third Army pushes through the remnants of Western Germany during mop-up operations across the Rhine. They stumble upon a battered airfield facility near Friedrichroda in Thuringia. Inside the hangar, soldiers freeze. Before them sits an aircraft unlike anything they've ever seen. No tail, no fuselage, just a sleek swept wing that resembles a stingray or a boomerang. A captured German engineer tells them these are jet-powered prototypes, flying wings designed to slip past radar and outrun any Allied fighter in the sky. What those American soldiers discovered that day was the Horten Ho 229, and it represented something terrifying. Nazi Germany had come within weeks of fielding a jet-powered flying wing fighter bomber that could have changed the nature of air warfare. This wasn't just another desperate German wonder weapon, this was a functional prototype of an aircraft concept that wouldn't be successfully deployed by any air force until the Northrop B-2 Spirit bomber flew 4 decades later. The Americans immediately understood they had to seize these prototypes and destroy all evidence before the Soviets realized what Germany had developed. Because the Ho 229 wasn't just advanced, it was a glimpse into the future of aerial combat that the United States would spend the next 50 years trying to perfect. The story of how this flying wing came to exist reveals a clash between two approaches to aviation design. On one side stood conventional aircraft engineering, fuselages, tails, vertical stabilizers, the entire architecture of flight that had evolved since the Wright brothers. On the other stood the Horten brothers' vision of pure aerodynamic efficiency, the belief that every component of an aircraft that didn't generate lift was dead weight creating drag. And in the desperate final years of World War II, when Germany needed a miracle, the Luftwaffe's commander Hermann Göring bet on the radical approach. In 1943, Göring issued a challenge to German aircraft designers. He called it the 3x1000 requirement. "Build me a bomber," he demanded, "that can carry 1,000 kilograms of bombs across 1,000 kilometers at 1,000 kilometers per hour." The strategic situation demanded nothing less. Allied bombers were systematically destroying Germany's industrial capacity. The Luftwaffe needed an aircraft fast enough to avoid interception with enough range to strike back at Britain, capable of carrying a meaningful bomb load. Every design bureau in Germany understood the problem. Jet engines could provide the speed, but they consumed fuel so voraciously that meeting the range requirement seemed impossible. Brothers Reimar and Walter Horten believed they had the answer. They'd been obsessed with flying wing design since the early 1930s, building gliders without tails or fuselages, aircraft that were nothing but wing from tip to tip. Their reasoning was elegant. A conventional aircraft wastes volume on structures that produce no lift. The fuselage carries the payload and crew but creates drag. The tail provides stability but adds weight and more drag. Strip all that away, integrate everything into a single aerodynamic surface, and you maximize lift while minimizing drag. The result would be an aircraft so efficient it could overcome the jet engine's fuel hunger. But the flying wing concept came with a fundamental problem that had prevented its widespread adoption: stability. On a conventional aircraft, the tail acts as a passive stabilizer. If the aircraft begins to slip sideways, the vertical stabilizer automatically produces a correcting force. If the nose pitches up or down, the horizontal stabilizer counteracts it. A pilot can fly a conventional aircraft with relatively simple controls because the aircraft naturally wants to return to stable flight. Remove the tail, and you remove that passive stability. A flying wing without active control becomes inherently unstable, prone to uncontrolled side slip and potentially flat spins. The pilot must constantly make corrections. The aircraft fights you. The Horten brothers addressed this through airfoil design and control surface innovation. They gave their wing a bell-shaped planform, long and thin with a high aspect ratio, which meant the aircraft's weight spread over a greater surface area. This provided inherent stability during a stall or engine failure, allowing the aircraft to slow down more controllably. For yaw control, since they had no vertical stabilizer, they used split ailerons called drag rudders. When the pilot needed to turn, these surfaces would deploy asymmetrically, creating more drag on one side than the other, effectively pulling the aircraft around. It was an active solution to replace the passive stability of a conventional tail. The wing itself used an unusual thickness-to-chord ratio, ranging from 15% at the root to 8% at the wingtips. The center section was built from welded steel tubing up to 160 millimeters in diameter, creating a strong internal structure. The outer wing spars were made of pine. The wings were skinned with thin plywood panels glued together with a sawdust mixture and covered with fireproof paint. This mixed construction reflected Germany's desperate material situation by 1944. Metal was scarce, so they used wood where possible. The wing had a single main spar penetrated by the jet engine inlets and a secondary spar for mounting the elevons, which combined the functions of elevators and ailerons. The Horten brothers calculated that this configuration, designed with a 7G load factor and a 1.8 safety rating, could handle 12.6 G's ultimate load. The wing sweep was 32 degrees measured from the nose to the start of each wingtip. This sweep served multiple purposes. It moved the center of pressure aft, providing pitch stability. It also provided yaw stability because when the aircraft yawed, one wing would present more frontal area than the other, creating differential drag that naturally corrected the yaw. Modern flying wings like the B-2 used this same principle. When the Horten brothers presented their H-INX design to Göring in 1943, they claimed it could meet his 3x1000 requirement. The Air Ministry was skeptical but intrigued. Göring himself was reportedly impressed enough to personally intervene, ordering 3 prototypes at a cost of 500,000 Reichsmarks. The Air Ministry even issued a provisional production order for 100 aircraft, but there was a complication. The Horten brothers operated from a small workshop. They had no facilities for mass production, so the Air Ministry assigned the manufacturing contract to Gothaer Wagenfabrik, an established company with production capacity. This arrangement created immediate problems. Gothaer was developing its own flying wing designs and allegedly worked to undermine the Horten project to favor its own programs. The Horten brothers found themselves sidelined as Gothaer's engineers took over design responsibility and made extensive changes. Gothaer redesigned the undercarriage to enable higher gross weight, modified the engine intakes, added ducting to cool the jet engine casings to prevent damage to adjacent wood, and implemented a simple ejection seat. The flying wing was evolving from the Horten brothers' pure concept into a production-engineered aircraft. The first prototype, designated H-INX 51, was an unpowered glider with fixed tricycle landing gear. It flew for the first time on March 1, 1944. The test pilot found the handling acceptable, proving the basic aerodynamics worked. But there was an accident when the pilot attempted to land without retracting a test instrument. Despite this, flight results were favorable enough to proceed with a powered version. The second prototype, HI-52, was fitted with twin Junkers Jumo 004B turbojet engines. These were not the Horten brothers' first choice. They had designed the aircraft around the BMW 003 engine, which was more compact, but the 003 wasn't ready. The Jumo 004 was larger in diameter, requiring Gothaer's engineers to modify the airframe's engine bays. Each Jumo 004B produced 8.83 kilonewtons of thrust, roughly 1,990 pounds force. These were axial flow turbojets, a relatively new technology, notoriously fuel-hungry and prone to reliability issues. They required frequent overhauls and were built with substandard materials due to Germany's strategic shortages of high-temperature alloys. The V2 prototype weighed approximately 9 tons loaded. It measured 7.4 meters along its center line, with a wingspan of 16.8 meters. The cockpit height was just 1.1 meters, making it extremely cramped. The pilot's head would brush the canopy. There was barely room for one crew member, making the addition of more equipment or weapons difficult. The aircraft was fitted with retractable tricycle landing gear, borrowing the nose gear from a Heinkel 177's tailwheel system. A drogue parachute slowed the aircraft on landing. The pilot sat on a primitive ejection seat, and a special pressure suit was developed by Draeger because the aircraft's ceiling was expected to reach 15,000 meters. On February 2, 1945, test pilot Lieutenant Erwin Ziller flew the H-952 for the first time under jet power at Oranienburg Airfield. The Horten brothers weren't present. They were occupied with another project, designing a turbojet-powered strategic bomber for the America Bomber competition, an even more ambitious program to create an aircraft capable of reaching the United States. All subsequent test flights were conducted by Gothair without the original designers present. Ziller flew 2 more test flights on February 2 and another on February 18th. Then, disaster struck. On February 18, 1945, during the third test flight, after approximately 45 minutes in the air at an altitude around 800 meters, one of the Jumo engines caught fire and failed. Witnesses saw Ziller put the aircraft into a dive and pull up several times, likely attempting to restart the failed engine. He made 4 complete turns at a 20-degree bank angle. He never used his radio. He never ejected. It's believed he was already unconscious from fumes from the burning engine. The aircraft crashed just outside the airfield boundary. Ziller died from his injuries. The Ho-229 V-2 was destroyed. This should have ended the program. Germany was collapsing. The Allies were advancing from both east and west, but Göring refused to give up. On March 12, 1945, nearly a week after the U.S. Army launched Operation Lumberjack to cross the Rhine, the Ho-229 was included in the Jaeger-Not program, the emergency fighter program, for accelerated production of inexpensive wonder weapons. The prototype workshop moved to Gothair Wagon Fabrik in Friedrichroda. Work started on the third prototype, the Ho-229 V-3, intended as a template for the pre-production series, the Ho-229 A-0 Dayfighters, of which 20 had been ordered. The V-3 was larger than previous prototypes with various refinements. It was to be powered by 2 Jumo 004C engines, each with 10% more thrust than the 004B. It would carry 2 Mk108 30mm cannons in the wing roots. Work also began on additional variants: the V-4 two-seat all-weather fighter, the V-5 night fighter version, the V-6 armament test prototype, and the V-7 two-seat trainer. Plans existed for even more ambitious versions. The Air Ministry envisioned a production run that would give the Luftwaffe an entirely new class of fighter bomber, but time had run out. In April 1945, Patton's Third Army overran the Gothair facility. They found 4 Horten prototypes. Of the 3 Ho-229S, the V-3 was nearest to completion, approximately 80% finished. The V-4 and V-5 were just bare center-section frameworks of welded steel tubing. The Americans immediately recognized the significance of what they'd captured. The V-3 was crated and shipped to the United States under Operation Paperclip, the program to seize German technology and scientists before the Soviets could claim them. American intelligence officers interrogated the engineers. A German engineer explained the concept: the flying wing configuration, the jet propulsion, the minimal radar cross-section, the high speed. The Americans realized they were looking at an aircraft design that could have presented serious problems if Germany had fielded it in numbers. The absence of a tail meant conventional tail warning radars would have difficulty detecting it. The smooth, blended shape would reflect radar energy poorly. The speed would have made interception difficult, and the structural efficiency of the flying wing meant it could carry a significant bomb load while maintaining high performance. The Ho-229 spent a brief period at RAF Farnborough in Britain. British engineers considered installing British jet engines to fly it, but the engine mounting was incompatible. British centrifugal flow engines had a larger diameter than German axial flow engines. It's uncertain whether the Americans ever ran the captured Jumo engines, though at one point they intended to fly the aircraft. Ultimately, they decided against it. The V-3 was too valuable as an intelligence asset to risk in flight testing. For decades, the Ho-229 V-3 remained in storage at various U.S. facilities. It eventually ended up at the Smithsonian National Air and Space Museum's Paul E. Garber Restoration Facility in Suitland, Maryland. In December 2011, the museum moved the Ho-229 into the active restoration area, where conservators began a detailed examination. The goal was to understand exactly how it was built, what materials were used, and whether it possessed any stealth characteristics, because by the early 21st century, rumors had circulated for years that the Horten brothers had intentionally designed the first stealth aircraft. These rumors originated with Reimar Horten himself. In 1983, after hearing about the American stealth program and the existence of aircraft like the F-117, Reimar claimed he had intended to add charcoal dust to the wood glue used in the Ho-229's construction. This charcoal, he said, would absorb electromagnetic waves, shielding the aircraft from British chain-home radar. This would have made the Ho-229 not just a flying wing, but a radar-absorbent flying wing, a true stealth aircraft created in 1944, decades before the concept was officially developed. The claim was explosive. If true, it meant Nazi Germany had developed radar-absorbent materials and understood low observable design principles 40 years before the B-2 Spirit. Aviation. Historians and aerospace engineers were skeptical. There was no documentation supporting the claim. No wartime records mentioned charcoal additives. No contemporary accounts from other engineers confirmed it. And the V-3 prototype itself showed no evidence of charcoal in the wood glue. But the legend persisted. In 2008, Northrop Grumman, the company that built the B-2 stealth bomber, partnered with television producer Michael Jorgensen and the National Geographic Channel to settle the question. They decided to build a full-scale reproduction of the Ho-229 V-3 and test its radar cross-section. Northrop committed significant resources to the project, spending approximately $250,000 and 2,500 man-hours. Their reproduction was primarily made of wood, unlike the original aircraft which had an extensive steel spaceframe. But the external shape was as accurate as they could make it based on measurements of the V-3. They took this reproduction to Northrop Grumman's radar cross-section test range at Tejon, California. They mounted the mock-up on a 15-meter pole and exposed it to electromagnetic energy sources from various angles, positioned 100 meters away. They used 3 frequencies in the 20 to 50 megahertz range, which corresponds to the high-frequency and very high-frequency bands that British chain-home radar operated in during World War II. The engineers recorded how much radar energy the Ho-229's shape reflected back to the receiver. Simultaneously, Northrop engineers tested the actual V-3 prototype's materials. They conducted electromagnetic tests on the multi-layer wood nose cone across a frequency range of 12 to 117 terahertz with a 10-micron wavelength. The nose cone was 19 millimeters thick, made from thin sheets of veneer. The team observed that the Ho-229's leading edge had the same electromagnetic characteristics as ordinary plywood, except for a slightly shorter bandwidth, likely due to oxidation of the wood over 60 years. They found no evidence of unusual absorption properties. The Smithsonian Institution then performed its own analysis. Museum conservators studied the V-3's materials in detail, taking samples of the wood, the glue, and the coatings. They found no evidence of carbon black or charcoal mixed into the adhesive. The fireproof paint was just fireproof paint, the wood was just wood, the glue was just glue. Reimar Horten's claim about radar-absorbent materials was not supported by physical evidence. The Ho-229 was not intentionally designed as a stealth aircraft, but the radar cross-section tests revealed something interesting anyway. When Northrop simulated the Ho-229 approaching the English coast from France, flying at 885 kilometers per hour at 15 to 30 meters altitude, the results showed the flying wing would have been detectable by chain-home radar at 80% of the range of a Messerschmitt Bf-109. The Ho-229's shape, even without radar-absorbent materials, did provide some reduction in radar signature compared to conventional aircraft, not enough to make it invisible, but enough to reduce detection range. This reduction came from basic shaping principles. A flying wing presents a smaller radar cross-section than a conventional aircraft because it lacks vertical stabilizers and horizontal stabilizers, which act as efficient radar reflectors. The blended wing body design means there are fewer sharp angles and edges where radar waves can bounce directly back to the receiver. The smooth curves scatter radar energy in multiple directions rather than returning it efficiently. However, the front and rear faces of the exposed jet engines provide significant radar returns comparable to propeller discs. The Ho-229 was not stealthy in the modern sense, but its shape was inherently more difficult to detect than conventional designs. American aerospace engineers and military intelligence officers understood the implications immediately when they examined the V-3 in 1945. They saw an aircraft design that was operationally viable and represented a significant leap in conceptual sophistication. The flying wing configuration offered real advantages: reduced drag for better fuel efficiency and range, a smaller radar signature, and the potential for high speed with relatively low-powered engines. These were exactly the characteristics the U.S. Air Force would need for future strategic bombers designed to penetrate Soviet air defenses. Jack Northrop, the American aviation pioneer, had been developing flying wing designs in parallel with the Horten brothers throughout the 1930s and 40s. His N-1M flew in 1940, his N-9M flew in 1942, his XB-35 flying wing bomber flew in 1946, though it was delayed by government interference and technical problems with its propellers. Northrop had been inspired by earlier Horten glider designs from the 1930s, and now, seeing the Ho-229, he gained confirmation that the concept could work with jet propulsion. The Ho-229's existence validated decades of Northrop's work, but flying wings remained extraordinarily difficult to fly without computerized flight control systems. The XB-35 suffered from severe vibration problems. The YB-49, the jet-powered version, demonstrated that flying wings were unstable platforms for accurate bombing because minor corrections in heading were difficult to make smoothly. A conventional aircraft with a vertical stabilizer can make small course adjustments easily. A flying wing must use asymmetric drag devices, which cause the aircraft to skid through the air rather than turning cleanly. For a bombardier trying to line up a target, this made precision bombing nearly impossible. The U.S. Air Force ultimately canceled Northrop's YB-49 program, though the decision was politically controversial. Air Force Secretary Stuart Symington wanted Northrop to merge with Convair, a deal Jack Northrop described as grossly unfair. According to Northrop, Symington told him he would be goddamn sorry if he didn't agree to the merger. Days later, Symington canceled all of Northrop's flying wing contracts. Northrop later admitted he perjured himself at hearings that investigated the matter, fearing the Air Force would blackball his company if he testified honestly. The flying wing concept was effectively dead in the United States for the next 30 years, but the Air Force never stopped thinking about the design. The captured Ho-229 remained in storage, studied periodically by engineers and intelligence analysts. The promise of the flying wing, extreme efficiency, inherent low observability, high performance, was too attractive to abandon. What was needed was a way to make it controllable, and by the 1970s, digital flight control systems finally made that possible. A fly-by-wire system could make the rapid corrections necessary to keep a flying wing stable, performing calculations and adjustments thousands of times per second, faster than any human pilot could react. When the B-2 Spirit stealth bomber first flew in 1989, it vindicated both Jack Northrop and the Horten brothers. The B-2 was a flying wing using the same fundamental design principles as the Ho-229, blended wing body configuration, no vertical stabilizers, control through differential drag and vectored thrust, but it added modern radar absorbent materials, composite structures, and computerized fly-by-wire control. It was what the Ho-229 could have become if Germany had possessed another decade of development time and technological advancement. A few months before Jack Northrop died in 1981, he was given security clearance to see a model of the B-2. He was elderly and ill, barely able to speak, but when he saw the aircraft he had envisioned 50 years earlier finally realized, he reportedly wrote a note. "I know why God has kept me alive for the last 25 years." The B-2 proved his concept worked, and buried in that validation was the shadow of the Horten Ho-229, the German flying wing that had almost changed the course of World War II and definitely changed the course of aviation history. Understanding why the Ho 229 mattered requires understanding what made 1944 such a desperate time for Germany. The Luftwaffe was being destroyed in a war of attrition it couldn't win. Allied strategic bombing had evolved from ineffective harassment in 1940 to systematic destruction by 1944. American daylight precision bombing targeted factories, oil refineries, and transportation infrastructure. British night area bombing incinerated cities. German fighter defenses shot down hundreds of Allied bombers. But the Allies simply built more. American industrial capacity was producing aircraft faster than Germany could shoot them down. The Luftwaffe's conventional piston-engine fighters were approaching their performance limits. The Bf-109 and Fw-190 were excellent aircraft, but they couldn't effectively intercept high-altitude B-17 and B-24 formations escorted by P-51 Mustangs. The American fighters had the range to accompany bombers deep into German territory and the performance to engage German interceptors on equal terms. German pilots were being killed faster than they could be replaced. Fuel shortages meant inadequate training for new pilots, so their survival rate dropped even further. The Luftwaffe needed something that could tip the balance, an aircraft so fast that Allied fighters couldn't catch it, or so efficient that it could operate despite fuel shortages, or so difficult to detect that it could avoid interception entirely. Jet propulsion offered the speed. The Messerschmitt Me 262 proved that. With a maximum speed of approximately 870 km per hour, the Me 262 was nearly 200 km per hour faster than any Allied piston engine. Fighter. Allied pilots couldn't chase down an Me 262 in level flight, but the Me 262 had serious vulnerabilities. Its engines were unreliable, failing catastrophically without warning. It consumed fuel so rapidly that its combat radius was limited. It was vulnerable during takeoff and landing when its speed advantage disappeared, and it was still visible on radar, so Allied controllers could vector fighters to its air bases and intercept it when it was most vulnerable. The Horten brothers argued their Ho 229 could address these limitations. The flying wing's efficiency meant greater range from the same fuel load, allowing more flexibility in operations. The lack of a tail meant a smaller radar signature, making it harder for ground controllers to track. The clean aerodynamics meant higher speed from the same engines and better acceleration, and the low-altitude performance would be exceptional because the wing's high aspect ratio provided excellent lift-to-drag ratio even at low speeds, allowing it to operate from shorter runways or conduct low-altitude penetration missions where it would be even harder to detect. Göring's 3x1000 requirement was specifically designed to enable strategic retaliation against Britain. German bombers had not effectively struck British targets since the Blitz of 1940 and 1941. By 1944, the Luftwaffe lacked the capability to mount sustained bombing campaigns against British industrial targets, but a fast, long-range jet bomber could change that. It could strike targets in England and return to bases in Germany, flying too fast for British fighters to intercept and potentially too stealthy to detect until it was too late. Even if it couldn't turn the tide of the war, it could exact revenge and potentially force the Allies to divert resources to defense. The Ho 229 came closer to meeting the 3x1000 requirement than any other design submitted. Its projected maximum speed was 960 km per hour at sea level, just short of the required 1,000. But at its cruising altitude of 12,000 meters, it could reach 977 km per hour, and some estimates suggested a never-exceed speed of exactly 1,000 km per hour. Its range was projected at 1,900 km, nearly double the required 1,000. And it could carry 1,000 kilograms of bombs internally or externally. No other aircraft design submitted to. Göring came close, but these were projections based on calculations and limited testing of the V-2 prototype. The V-2 flew only a handful of times before crashing. The V-3 never flew. We don't know if the Ho 229 would have actually achieved these performance figures in operational service. German projections for aircraft performance were often optimistic, and the severe material shortages of late-war Germany meant that production aircraft rarely matched prototype specifications. The Jumo 004 engines were notorious for failing after just 10 to 25 hours of operation. A Ho 229 dependent on these engines would need frequent overhauls, and Germany lacked the industrial capacity to support that in 1945. Moreover, the handling characteristics would have posed severe challenges for Luftwaffe pilots. The V-2's test flights were conducted by an experienced test pilot on a perfect airfield under controlled conditions, and even he couldn't save the aircraft when an engine failed. Combat operations would require pilots to fly the Ho 229 in bad weather, under enemy fire, with battle damage during night operations, while maneuvering aggressively to avoid interceptors. The flying wing's inherent instability meant that any distraction, any moment of inattention, could result in loss of control. And the cramped cockpit meant the pilot would be fighting the aircraft for hours during long-range missions. Even the armament was problematic. The planned two Mk108 30mm cannons were powerful weapons, each firing a 518-gram high-explosive shell at a rate of 650 rounds per minute. Against Allied bombers, they were devastatingly effective. A few hits would destroy a B-17, but the Mk108 had a very low muzzle velocity, just 540 meters per second, which gave the shells a pronounced ballistic arc. This made aiming difficult, especially from the Ho 229's unstable platform, and for ground attack missions, two cannons provided limited firepower compared to aircraft like the FQW-190, which could carry bombs, rockets, and multiple cannons simultaneously. The American evaluation team that examined the captured V-3 understood all of these limitations. They noted the cramped cockpit, the marginal stability, the unreliable engines, the limited armament, the vulnerability of the wooden structure to combat damage. But they also recognized the conceptual sophistication. The Germans had identified the right problems: fuel, efficiency, speed, observability, and proposed solutions that were fundamentally sound even if the execution was premature. The Ho 229 was a bridge between World War II aircraft design and the jet age that would follow. When news of the capture reached the Soviet Union, Stalin's intelligence services immediately began demanding information about the German flying wing. Soviet aircraft designers had also been experimenting with tailless and flying wing configurations, but they lagged behind German developments. The Soviets had captured substantial German aviation technology, including complete examples of the Me-262 and R-234 jet aircraft, and they were reverse engineering these designs for their own programs. But they had not captured an intact Ho 229, and they wanted one desperately. American intelligence officers made sure the Soviets never got the chance. The incomplete V-4 and V-5 prototypes were deliberately destroyed. Documentation was seized and classified. The engineers who had worked on the project were interrogated and in some cases recruited to work for American aviation companies under Operation Paperclip. The United States was determined to maintain exclusive access to the most advanced German aviation technology because the wartime alliance with the Soviet Union was already fraying and the early Cold War was beginning. The Horten brothers themselves had mixed fates. They were not arrested or prosecuted as war criminals because they had not been party members and their work was purely technical. After the war, Reimar Horten moved to Argentina, where he continued designing flying wing aircraft for the Argentine Air Force, though few of these projects were built. Walter Horten remained in Germany and worked in various engineering roles. Both brothers maintained that the Ho 229 could have been decisive if it had been fielded in numbers earlier in the war, though most historians consider this claim exaggerated. But what if Germany had succeeded? What if the Ho 229 had entered production in late 1944 instead of early 1945, giving the Luftwaffe 6 months to field operational squadrons? The scenario is worth considering because it reveals both the aircraft's potential and its limitations. Assume Germany had managed to build and deliver 50 Ho 229 aircraft by January 1945. These would be distributed to specialized units tasked with either bomber interception or strategic strikes against Britain. What would have happened? For bomber interception, the Ho-229 would have presented serious problems for Allied bomber formations. Its speed would have allowed it to climb rapidly to intercept altitude, make a high-speed attack pass, and escape before escort fighters could engage. The two Mk-108 cannons would be lethal against bombers. A few hits would destroy a B-17 or B-24. Allied gunners would have difficulty tracking and hitting an aircraft closing at over 900 kilometers per hour. The Ho-229 could theoretically make multiple attack passes against a bomber formation using its speed and climb rate to avoid pursuit. But this scenario assumes everything works perfectly. In reality, the Jumo 004 engines would suffer frequent failures. Many Ho-229s would never complete a mission due to mechanical problems. Those that did would be vulnerable during takeoff and landing when their speed advantage disappeared. Allied intelligence would quickly identify the operating bases and pattern of attacks, allowing fighters to position for interception during the vulnerable phases. And the Ho-229's limited ammunition, the Mk-108 carried only 60 rounds per gun, meant each aircraft could make only a few attack passes before running out of ammunition and having to return to base. For strategic strikes against Britain, the Ho-229's range and speed would allow it to reach targets that had been beyond German capability since 1941. London, industrial centers in the Midlands, ports and airfields would all be vulnerable. The Ho-229 could conduct hit-and-run raids, striking at night or in bad weather when its small radar cross-section would make interception difficult. But the 1,000-kilogram bomb load was relatively small, comparable to what a single B-17 carried, and the Allies were sending hundreds of B-17s on raids. A force of 50 Ho-229s could not inflict damage comparable to Allied strategic bombing. At best, they could force the British to divert night fighters and maintain blackout conditions, imposing costs without achieving strategic effect. The real impact would have been psychological and developmental. If Allied aircrews encountered an aircraft they couldn't intercept or engage effectively, it would have undermined confidence in air superiority. Allied commanders would have been forced to divert resources to counter the threat, potentially slowing the bombing campaign, and the existence of an operational flying wing jet fighter would have accelerated Allied development of similar aircraft and tactics to counter them. The war might have lasted weeks or months longer, but the outcome would not have changed. Germany's strategic position was hopeless by 1945, and no single weapon system could alter that. What the Ho-229 really represented was desperation. Germany was losing the war of production. The Allies could afford to develop weapons incrementally, testing thoroughly, accepting delays, and refining designs through multiple iterations. Germany had no such luxury. Every aircraft design had to be a potential war winner, something so superior to Allied equivalents that it could compensate for Germany's industrial and numerical inferiority. This drove German engineers to pursue radical, high-risk concepts like the flying wing, the rocket interceptor, the swept-wing jet fighter, and dozens of other advanced designs. Some of these concepts were genuinely brilliant, decades ahead of their time. Others were impractical fantasy, and even the brilliant ones came too late to matter. The Ho-229 falls into the category of brilliant but premature. The core concept was sound, the engineering was sophisticated, the performance predictions were plausible, but the technology required to make it reliable and safe did not exist in 1945. It would take another 40 years of development in materials science, engine technology, and flight control systems before flying wing aircraft could be deployed successfully. When the B-2 Spirit finally entered service in 1989, it represented the culmination of everything the Horten brothers had attempted, refined through decades of additional engineering. Some historians speculate about whether the Ho-229 influenced American aerospace development directly. Did American engineers study the captured V-3 and incorporate its design principles into post-war aircraft? The evidence suggests the answer is nuanced. American designers were already pursuing flying wing concepts independently through Jack Northrop's work. The XB-35 and YB-49 were developed in parallel with the Ho-229 without direct knowledge of the German aircraft. But after 1945, American engineers had access to the Ho-229 and could examine how the Germans had solved specific problems: the engine mounting, the control surface arrangement, the structural design, the materials used. The National Advisory Committee for Aeronautics conducted wind tunnel tests on the Ho-229 V3 shape and documented its aerodynamic characteristics. This data entered the body of knowledge that American aerospace engineers could draw upon when designing their own aircraft. Northrop engineers almost certainly studied the Ho-229 when developing concepts that eventually led to the B-2. The similarities are too striking to be purely coincidental: the swept wing planform, the engine placement, the blended center section. But the B-2 is not a copy of the Ho-229. It's a product of independent development that arrived at similar conclusions because the underlying physics of efficient flight are universal. One persistent question is whether Germany could have developed a truly stealthy version of the Ho-229 if the war had continued. Reimar Horten's claims about charcoal additives suggest he was thinking about radar signature reduction, even if he never implemented it. German engineers understood the principles of radar and how it detected aircraft. They knew that shaping and materials could affect radar returns, but they lacked the theoretical framework for designing low observable aircraft, the computational tools for modeling radar cross-sections, and the materials science for creating effective radar-absorbent structures. Modern stealth aircraft like the F-117 and B-2 rely on precise geometric shaping calculated using computational electromagnetic modeling. Every angle, every surface, every seam is designed to scatter radar energy away from the receiver or absorb it before it can return. The shapes are often aerodynamically inefficient, requiring computerized flight control to keep the aircraft stable. The materials are exotic composites and coatings that absorb specific radar frequencies. The entire aircraft must be treated as an integrated system where every component contributes to signature reduction. Germany in 1945 had none of these capabilities. Even if Reimar Horten had added charcoal to the wood glue, the effect would have been minimal. Radar-absorbent materials work by converting electromagnetic energy into heat through dielectric or magnetic losses within the material. Carbon black can provide some absorption, but only if applied in the correct thickness, pattern, and configuration for specific frequencies. Random distribution of charcoal dust in wood glue would not create effective absorption. It would be like trying to build a computer by randomly scattering transistors in plastic. The components exist, but without precise arrangement and integration, they don't function. The real stealth characteristic of the Ho-229 was purely incidental, its shape, and even that provided only marginal benefit against World War II-era radar. The aircraft would still have been detected and tracked, just at slightly reduced range. Against modern radar systems operating at higher frequencies with greater sensitivity and computational processing, the Ho-229 would have been easily detected despite its flying wing configuration. True stealth requires optimization for specific threat radars, and that level of design sophistication was decades away. What made the Ho-229's capture so significant to American intelligence was not that it revealed revolutionary stealth technology, but that it confirmed the viability of flying wing-jet aircraft for military operations. Throughout the late 1940s and 1950s, American military planners debated whether flying wings were practical. The crashes and instability problems of the XB-35 and YB-49 suggested they might be too dangerous to operate. But the Ho-229 demonstrated that the Germans had flown a jet-powered flying wing successfully multiple times before the crash. The design worked, it could be done. The problems were engineering challenges, not fundamental impossibilities. This knowledge influenced strategic thinking during the early Cold War. The United States needed bomber aircraft capable of penetrating Soviet air defenses to deliver nuclear weapons. Conventional bombers like the B-36 and B-52 were large, relatively slow, and presented obvious radar signatures. They relied on altitude, electronic countermeasures, and escort fighters for survival. But a flying wing bomber would be faster, more efficient, and harder to detect. It would represent a quantum leap in penetration capability. The challenge was making it controllable and reliable. The solution came from an unexpected direction: the advent of digital computers and fly-by-wire flight control systems. In the 1960s and 1970s, aerospace engineers began experimenting with aircraft that were deliberately designed to be aerodynamically unstable, relying on computerized systems to maintain control. The computer could react faster than any human pilot, making thousands of corrections per second to keep the aircraft stable. This opened up new design possibilities, including efficient configurations like flying wings that would be impossible to fly manually. By the time Northrop began developing what would become the B-2 Spirit in the late 1970s, all the necessary technologies had matured. Digital flight control computers were reliable and compact. Radar-absorbent materials had been developed and tested. Computational tools could model radar cross-sections before building hardware. Composite materials provided structural strength without the weight penalties of metal. And turbofan engines offered far better fuel efficiency and reliability than the primitive turbojets of World War II. The flying wing concept could finally be realized properly. When the B-2 first flew on July 17, 1989, it vindicated everyone who had believed in the flying wing concept: Jack Northrop, the Horton brothers, and generations of aerospace engineers who had struggled with the challenges. The B-2 demonstrated everything the HO-229 had promised: exceptional range due to aerodynamic efficiency, high speed, and a radar signature so small that it could penetrate sophisticated air defense networks. It was what the HO-229 could have become with 40 years of additional development. But the B-2 also revealed the true cost of flying wing technology. The aircraft was extraordinarily expensive, with a total program cost exceeding $44 billion for just 21 aircraft, more than $2 billion per aircraft. The maintenance requirements were severe, with each aircraft requiring extensive care of its radar-absorbent coatings after every flight. The program suffered numerous delays and technical problems during development, and the operational limitations, particularly in adverse weather and during certain maneuvers, remained challenging despite advanced technology. This raises a counterfactual question. If Germany had successfully fielded the HO-229 in significant numbers, would the Allied response have accelerated flying wing development by a decade or more? Would the United States have pursued a stealth bomber program in the 1950s instead of the 1970s? The answer is probably no, because the enabling technologies, computers, materials, manufacturing techniques, didn't exist yet. You cannot build a stealth aircraft without the tools to design and produce it, no matter how motivated you are. The Allies might have intensified research into flying wings, but they could not have deployed operational aircraft significantly earlier than they did historically. What the Allies would have done is develop tactics and systems to counter the HO-229 specifically. This was Britain's specialty, developing countermeasures faster than Germany could deploy new weapons. When Germany introduced the V-1 flying bomb, Britain quickly organized fighter patrols that learned to shoot them down or tip them off course. When Germany deployed the V-2 ballistic missile, Britain developed predictive targeting analysis to locate launch sites. If the HO-229 had become operational, the Royal Air Force would have studied its performance envelope, identified vulnerabilities, and exploited them. The most obvious vulnerability was the engine reliability. Junkers Jumo 004 engines failed catastrophically and frequently. They had a mean time between failures of just 10 to 25 hours, depending on operating conditions. For the HO-229, which needed both engines functioning to maintain control, any engine failure was potentially fatal, as demonstrated by the V-2's crash. Allied intelligence would have quickly recognized this weakness. Instead of trying to engage HO-229 aircraft in air-to-air combat, where their speed provided advantage, Allied fighters would have been positioned near German airfields to attack during takeoff and landing. Bombers would have struck the air bases themselves, cratering runways and destroying parked aircraft. the fuel consumption issue presented another vulnerability. The Ho-229's range of 1,900 kilometers sounds impressive, but that assumed optimal conditions and careful fuel management. Combat operations, high-speed maneuvering, climbing to altitude, extended loitering would dramatically reduce effective range. An Ho-229 attempting to strike targets in Britain would have minimal time over target before needing to return to base. Any damage to the aircraft, any navigation errors, any combat engagement would consume precious fuel. Allied planners would have recognized that forcing Ho-229s to maneuver defensively would exhaust their fuel and force them to break off attacks or risk running dry on the return flight. The limited armament was a third weakness. 2 Mk-108 cannons with 60 rounds each gave the Ho-229 just enough ammunition for a few attack passes. Against bomber formations protected by hundreds of escort fighters, an Ho-229 pilot would have to penetrate the escort screen, identify and close on a bomber target, achieve a firing solution while traveling at over 900 kilometers per hour relative to the target, fire accurately with the low-velocity Mk-108, and then escape before Allied fighters could react. This was extraordinarily difficult even for veteran pilots. For the poorly trained replacement pilots Germany was fielding by late 1944, it would have been nearly impossible. These vulnerabilities explain why the Ho-229, even if successfully deployed, would not have changed the war's outcome. Germany's strategic situation by 1944 was fundamentally hopeless. The Allies had achieved air superiority through sheer numerical advantage, superior pilot training, abundant fuel supplies, and overwhelming industrial production. The Luftwaffe was being ground down in a war of attrition it could not win. Individual weapon systems, no matter how advanced, could not overcome these structural disadvantages. The Ho-229 might have imposed higher costs on Allied bomber formations, but it could not have stopped the bombing campaign or prevented Germany's defeat. What the Ho-229 did accomplish was demonstrating that radical innovation was possible, even under desperate circumstances. The Horten brothers took an unconventional concept, the flying wing, and developed it into a functional military aircraft using limited resources in a collapsing state. They solved difficult engineering problems related to stability, control, and structure. They proved the concept could fly. This was a genuine achievement, even if it came too late to affect the war. The legacy of the Ho-229 extends beyond its technical specifications or historical impact. It represents a particular approach to aerospace design, pursuing efficiency through radical configuration changes rather than incremental improvements to existing designs. This philosophy influenced post-war aircraft development, particularly in the United States, where designers continually explored unconventional configurations, delta wings, forward-swept wings, canards, blended wing bodies, searching for breakthrough performance improvements. Some of these concepts succeeded spectacularly. The delta wing configuration used on aircraft like the Mirage and Concorde provided excellent high-speed performance. The blended wing body approach used on the F-16 and modern airliners improved fuel efficiency, but many radical concepts failed or proved impractical. Forward-swept wings required exotic composite materials to prevent structural failure. Tailless delta configurations had poor low-speed handling. Canard configurations suffered from complex aerodynamic interactions. The history of aerospace design is littered with brilliant ideas that didn't work as hoped. The Ho-229 occupies an interesting position in this history. It was a radical concept that worked, barely, with 1940s technology. It crashed due to engine failure rather than aerodynamic problems. The design itself was sound even if the execution was premature. This suggests that the Horten brothers were genuinely ahead of their time, thinking about aircraft design in ways that wouldn't become mainstream for decades. They understood that conventional configurations carried inherent penalties in drag and weight, and they were willing to accept the challenges of unconventional designs to eliminate those penalties. Modern aerospace engineers still grapple with the same trade-offs the Horten brothers faced. The flying wing configuration offers theoretical advantages in efficiency and signature reduction, but it imposes severe penalties in stability, control, and operational flexibility. The B-2 Spirit proves the concept can work with sufficient technological sophistication, but at enormous cost. The question remains whether flying wings will ever become common in military or civilian aviation, or whether they will remain specialized tools for specific missions. One area where flying wing designs show promise is in large cargo and transport aircraft. Boeing and NASA have studied blended wing-body concepts for next-generation airliners that could carry hundreds of passengers more efficiently than conventional tube-and-wing aircraft. These designs would provide more interior volume, lower fuel consumption, and reduced noise. But they face significant challenges in certification, passenger acceptance, and airport compatibility. A flying wing transport requires different boarding procedures, different baggage handling, different maintenance access. These practical considerations often outweigh theoretical efficiency advantages. For military applications, the flying wing concept has found a secure niche in strategic bombers and unmanned reconnaissance aircraft. The B-2 Spirit has been followed by the B-21 Raider, another flying wing stealth bomber that will replace the B-1 and B-2 fleets. The RQ-170 Sentinel reconnaissance drone uses a flying wing configuration for persistence and low observability. These aircraft prove that the concept the Horten brothers pioneered remains relevant 80 years later. But they also demonstrate that flying wings require enormous investment in technology and infrastructure to be practical. The story of the HO-229 also illustrates how technological development is path-dependent and historically contingent. If the Horten brothers had worked in a different country at a different time, they might never have built their flying wing fighter. Germany's specific situation, facing overwhelming Allied air superiority while possessing advanced jet engine technology and a culture that encouraged radical innovation, created the conditions where the HO-229 could be developed. In a stable, peacetime environment, conventional designs would have been preferred as less risky. In a less technologically advanced nation, the necessary jet engines wouldn't have existed. The HO-229 emerged from a unique confluence of necessity, capability, and opportunity. This historical contingency makes alternate history speculation particularly difficult. We cannot simply say, if the HO-229 had been developed earlier, without considering what other historical factors would need to change. Developing the HO-229 earlier would require Germany to have possessed mature jet engine technology earlier, which would require different decisions about research priorities in the 1930s, which would require different assessments of strategic needs, which would require different political and military leadership. The counterfactual spirals outward until we're imagining a fundamentally different World War II. What we can say definitively is that the capture of the HO-229 V3 provided the United States with valuable technical intelligence about German aerospace capabilities and confirmed the viability of flying wing designs. American engineers studied the aircraft, documented its construction, tested its materials, and incorporated lessons learned into their own programs. This knowledge transfer was one of the many ways that German wartime technology influenced post-war American aerospace development, along with captured rocket scientists, jet engines, swept-wing research, and numerous other technologies. The Smithsonian's preservation and display of the HO-229 V3 ensures that future generations can study this remarkable aircraft. The nearly complete prototype, with its wooden wings and steel tubular center section, represents a moment when aerospace design could have branched in a radically different direction. The fact that it took another 40 years for flying wings to succeed demonstrates both how prescient the Horten brothers' vision was and how difficult the engineering challenges were. They were right about the destination, but too early for the journey. For Russell Lee, the chair of the Aeronautics Department at the National Air and Space Museum, the HO-229 represents something beyond just technical achievement. In his view, the aircraft symbolizes how talented engineers in desperate circumstances can create remarkable innovations even while serving evil regimes. The Horten brothers were not Nazis, they were not party members, and their work was purely technical. But they worked for a Nazi government, and their aircraft would have been used to prolong a war of aggression and genocide. This moral ambiguity is uncomfortable but important. We can acknowledge the engineering brilliance of the Ho 229 while condemning the purposes it would have served. This tension between technical achievement and moral context runs throughout the history of weapons development. Many of the technologies we use today, rockets, jet engines, computers, radar, were developed or accelerated by military necessity during World War II. German engineers, American engineers, British engineers, Soviet engineers all contributed to advancing technology while simultaneously working to kill each other. The knowledge they generated persists regardless of the circumstances of its creation, and we benefit from their work while trying to understand the context in which it occurred. The Ho 229 in particular forces us to confront this complexity. It's visually striking, technically sophisticated, and historically significant. It represents genuine innovation and problem-solving at the highest level, but it also represents desperation, destruction, and a regime's attempt to avoid the consequences of its own evil. We can study it, preserve it, and learn from it while never forgetting what it was meant to do and who would have been harmed if it had succeeded. When American soldiers first entered that hangar in April 1945 and saw the Ho 229 prototypes, they were looking at more than just captured enemy equipment. They were witnessing the end of Germany's technological war effort, the moment when all the desperate innovation and radical experimentation came to nothing because the war was lost. The flying wings sitting incomplete in their workshops represented roads not taken, futures that would never occur, ideas that arrived too late. Those soldiers couldn't have known that decades later their own country would build flying wing bombers based on similar principles, or that the strange aircraft they were creating for shipment to America would end up as one of the most significant artifacts in aviation history. The German engineer who explained the Ho 229's design to the American soldiers might have felt pride in the aircraft's sophistication or bitterness about its incomplete state. Perhaps he was simply relieved the war was over. We don't know his name or what became of him. But his explanation, that these flying wings were jet-powered prototypes designed to slip past radar and outrun any Allied fighter, must have stunned the American soldiers who were standing in front of an aircraft that looked like nothing they had ever seen, like something from the future that had somehow materialized in a German workshop in 1945. That moment of recognition, when American military personnel realized they were looking at technology that exceeded their own capabilities in certain respects, must have been both exciting and disturbing. Exciting because it represented captured knowledge that could accelerate American aerospace development. Disturbing because it revealed that Germany, even while losing the war catastrophically, was still capable of producing advanced weapons that could have complicated the Allied victory if deployed earlier or in greater numbers. The Ho 229 was a reminder that technological superiority was temporary and relative, that other nations and other engineers could produce innovations that challenged American dominance. This realization shaped American Cold War strategy. The United States committed enormous resources to maintaining technological superiority over the Soviet Union, investing in research, development, and rapid deployment of advanced weapons systems. The Air Force in particular embraced high-risk, high-payoff technology programs, accepting failures and cost overruns as the price of innovation. This approach eventually produced the stealth aircraft, precision-guided weapons, and advanced sensors that gave the United States decisive advantages in conflicts from the Gulf War through the present. But it began with captured German technology and the recognition that innovation could emerge from unexpected places. The Ho 229's influence on American aerospace thinking was therefore both direct and indirect. Directly, it provided technical data about flying wing design, materials, and construction techniques. Indirectly, it reinforced the lesson that radical innovation required organizational support, adequate resources, and willingness to pursue unconventional ideas, even when they contradicted established doctrine. The German experience showed both what to do, encourage innovation, test new concepts, iterate rapidly, and what not to do, pursue too many programs simultaneously, deploy immature technology prematurely, prioritize novelty over reliability. American aerospace companies absorbed these lessons in different ways. Lockheed's Skunk Works, which developed the U-2, SR-71, and F-117, embraced the German model of small teams working on classified projects with minimal bureaucratic oversight. Boeing and other major contractors took a different approach, relying on large-scale systems engineering and extensive testing before deployment. Both models succeeded in different contexts, proving there was no single path to innovation. Jack Northrop's company fell somewhere between these extremes. Northrop pursued radical designs but struggled with program management and political challenges. The Flying Wing projects were technically successful, but commercially and politically unsuccessful until decades after his death. This suggests that technical excellence alone is insufficient. Successful innovation requires matching the right technology with the right mission at the right time, with adequate organizational and political support. The Horton brothers and Jack Northrop both learned this lesson painfully, watching their flying wings canceled or incomplete while conventional designs dominated. The modern context makes the HO-229 story even more relevant. Contemporary aerospace programs face similar challenges: how to incorporate radical new technologies, how to balance innovation against reliability, how to justify enormous development costs, how to deploy advanced capabilities before adversaries develop countermeasures. The B-21 Raider program, which is developing America's next generation of stealth bombers, faces many of the same questions that surrounded the HO-229 80 years ago. Is the flying wing configuration still the best choice? Can modern materials and systems overcome the inherent stability challenges? Will the enormous cost be justified by operational advantages? These questions have no easy answers, which is why the HO-229 remains studied and debated by aerospace engineers, military historians, and aviation enthusiasts. It represents a crystallized moment of possibility when technology enabled a leap forward that circumstances prevented from being realized. The aircraft in the Smithsonian Museum is simultaneously a relic of failed ambition and a prophecy of successful innovation, a reminder that good ideas often arrive before the world is ready for them. For visitors to the Udvar-Hazy Center who stand before the HO-229 V3, the aircraft poses questions about technological development, historical contingency, and the relationship between innovation and conflict. Why does this wooden and steel prototype matter? Why preserve it? What does it teach us? The answers are complex and multifaceted. It matters because it represents human creativity applied to solving difficult problems. It should be preserved because it documents a unique moment in aviation history. It teaches us that innovation is unpredictable, that good ideas can emerge anywhere, and that success requires more than technical excellence. The HO-229 also serves as a cautionary tale about the limits of technology. Germany developed numerous advanced weapons in the final years of World War II: jet fighters, rocket interceptors, guided missiles, super heavy tanks, and none of them prevented defeat. Innovation cannot overcome fundamental strategic disadvantages like inadequate resources, poor strategy, and overwhelming enemy numerical superiority. This lesson remains relevant in contemporary conflicts where technologically advanced militaries discover that precision weapons and stealth aircraft cannot guarantee victory against determined adversaries fighting on favorable terrain. At the same time, the HO-229 demonstrates that technological advantages do matter, just not always in the ways or timeframes their developers expect. The flying wing concept proved valuable eventually, just not for Germany in 1945. The principles of signature reduction and aerodynamic efficiency that the Horton brothers explored became foundational to later aircraft development. Their work had impact, just not the impact they intended. This delayed payoff is common in aerospace technology, where ideas often require decades to mature from concept to operational capability. Understanding the HO-229's place in aviation history requires appreciating both what it achieved and what it failed to achieve. It achieved technical validation of flying wing design principles. It demonstrated that jet-powered tailless aircraft could fly successfully. It proved that unconventional configurations could offer real performance advantages. But it failed to influence World War II's outcome. It failed to protect Germany from defeat. It failed to enter production or operational service. These failures were not primarily technical failures. They were failures of timing, resources, and strategic context. This distinction between technical success and operational failure characterizes many advanced weapons programs. The technology works, sometimes brilliantly, but it doesn't accomplish its intended mission because the mission was unrealistic, the operational environment was unsuitable, or the broader strategic situation made success impossible, regardless of technical performance. Modern military procurement struggles with this same challenge: how to identify which technologies will provide genuine operational advantages versus which are merely technically impressive but operationally marginal. The Ho-229 program cost Germany approximately 500,000 Reichsmarks and consumed resources that could have been used for more practical purposes. Those resources, the steel, wood, skilled labor, engineering time, and scarce jet engines, might have produced more conventional aircraft that would have had greater immediate impact. This opportunity cost is the hidden price of innovation. Every radical new program diverts resources from proven designs. Sometimes the gamble pays off spectacularly. Usually it doesn't. Germany in 1944 and 1945 was making desperate gambles because conventional approaches had already failed, but desperation is a poor basis for research and development strategy. Allied intelligence officers who evaluated the captured Ho-229 and other German advanced projects concluded that Germany had wasted significant resources pursuing too many experimental weapons simultaneously. German industry was developing dozens of jet aircraft designs, multiple rocket programs, several super heavy tank projects, and numerous other advanced weapons, often with overlapping capabilities and competing requirements. This diffusion of effort meant none of the programs received adequate resources or attention. A more focused approach concentrating on a few high-priority projects might have been more effective, though still insufficient to change the war's outcome. This analysis influenced post-war American weapons development. The United States pursued advanced technology aggressively, but tried to maintain focus and avoid the scattershot approach that characterized late-war German programs. There were still failures and false starts. The XB-70 Valkyrie bomber, the F-111 fighter bombers' troubled development, the many canceled missile programs, but the overall approach emphasized fewer, better-supported programs rather than many competing experimental efforts. Whether this approach was actually superior remains debatable, but it was consciously chosen based on lessons learned from studying German mistakes. The Ho-229's specific contributions to American aerospace knowledge are difficult to quantify precisely because the influence was diffuse and occurred over decades. American engineers who studied the captured V-3 in the late 1940s documented what they learned in classified reports that informed later design efforts. Some of these engineers went on to work on flying wing projects at Northrop or other companies, bringing their knowledge of German solutions to American problems. Other engineers used the Ho-229 as a reference point for evaluating their own designs or validating their calculations. The aircraft became part of the collective knowledge base that aerospace engineers drew upon, one data point among thousands that shaped thinking about what was possible. This diffuse influence is characteristic of how captured technology affects development in the capturing country. Very rarely does a captured weapon lead to direct copying or immediate deployment. More commonly, it provides ideas, validates concepts, reveals approaches that hadn't been considered, and identifies dead ends worth avoiding. The Ho-229 functioned in all these ways. It validated that flying wings could work with jets. It revealed German approaches to solving stability and control problems. It suggested that signature reduction through shaping was possible even without advanced materials. And it demonstrated that wooden construction could be viable for high-performance aircraft when metal was scarce. Each of these lessons had value even though none led directly to American aircraft that copied the Ho-229's design. American engineers pursuing flying wing concepts could reference the German work as proof of concept. Designers working on signature reduction could study the Ho 229 shape and understand how geometry affects radar returns. Structural engineers could examine the mixed steel and wood construction and consider whether similar approaches might be useful in American contexts. The value was in expanding the space of known possibilities rather than providing a blueprint to copy. This is ultimately the most important legacy of the Horten Ho 229. It expanded the envelope of what aerospace engineers knew was achievable. Before the Ho 229, flying wing jet fighters were theoretical. After examining the captured V-3, they were demonstrated fact. This shift from theoretical to proven changes how engineers think about design problems. It provides a concrete example that can be studied, measured, and understood. It removes uncertainty about whether the basic concept works, allowing focus to shift to how to make it work better. The B-2 Spirit's designers knew the flying wing concept was viable, partly because the Ho 229 had proven it 40 years earlier. They didn't copy the German design. The B-2 is far more sophisticated in every respect, but they knew the fundamental approach was sound. This knowledge shortened development time, reduced risk, and increased confidence that the massive investment in the B-2 program would produce a functional aircraft. In this indirect way, the Ho 229 contributed to one of America's most capable military aircraft, helping to validate the very concept it was meant to use against Allied forces. Standing before the Ho 229 V-3 in the Udvar-Hazy Center today, visitors see an aircraft that never completed its intended mission, but nevertheless succeeded in proving an idea. They see craftsmanship in the carefully constructed wooden wings, ambition in the swept planform, sophistication in the engine mounting and control surfaces, and failure in the fact that this prototype never flew and the war it was meant to influence ended decades ago. All of these elements coexist in the silent artifact, a machine that embodies both human ingenuity and human conflict, technical achievement and strategic failure, vision and desperation. The American soldiers who captured this aircraft in April 1945 preserved something valuable even if they couldn't fully understand its significance at the time. They ensured that the Ho 229 would be studied, documented, and eventually displayed for future generations. In doing so, they allowed the Horten brothers' work to have an impact far beyond what either the designers or the captors could have imagined. The flying wing concept that seemed so radical and risky in 1945 became mainstream aerospace technology by the end of the 20th century, and the Ho 229 stands as evidence of the vision that made that transformation possible. This is what happens when you capture an enemy's innovation rather than destroying it. The ideas persist, cross borders, influence future development, and eventually contribute to technologies that serve purposes entirely different from their original intent. The Ho 229 was designed to help Germany win World War II. It ended up helping America develop stealth bombers for the Cold War. History is full of such ironies, where technologies transcend their original purpose and find applications their creators never imagined. The Ho 229 story confirms what aerospace historians have long understood. Innovation is rarely the product of a single nation, individual, or program. Instead, it emerges from the global community of engineers building on each other's work, learning from successes and failures, competing and collaborating across borders and decades. The Horten brothers built on earlier flying wing research by Hugo Junkers and others. Jack Northrop studied the Horten gliders and built on their ideas. American engineers examined the captured Ho 229 and incorporated lessons into the B-2. Chinese engineers have since examined the B-2 and developed their own stealth aircraft. The cycle of innovation continues, with each generation standing on the shoulders of previous work. In this broader context, the Ho 229 is one thread in a much larger tapestry of aerospace development. It's an important thread, a visible and significant one, but not the sole determinant of outcomes. If the Ho 229 had never been built, Flying wing aircraft would still have been developed eventually because the underlying physics and engineering principles would remain valid. But the Ho-229's existence accelerated that development by providing a concrete demonstration of what was possible, and by surviving as a physical artifact that engineers could study for decades afterward. This is the ultimate irony of the Ho-229. Designed as a weapon to change the outcome of World War II, it instead became a tool for advancing aerospace knowledge in the post-war period. Its greatest impact came not from the few test flights it made in 1944 and 1945, but from the 6 decades it spent in storage and study in America, silently influencing generations of engineers who examined its structure, studied its design, and incorporated its lessons into their own work. The aircraft achieved more through capture and preservation than it ever could have through operational deployment. When German engineers designed the Horten Ho-229, they imagined it flying against Allied bombers, striking targets in Britain, turning the tide of the air war. When American soldiers captured it, they saw a trophy of victory and a source of technical intelligence. When Smithsonian curators preserved it, they recognized a significant artifact of aviation history. And when modern visitors view it in the museum, they see all of these things simultaneously: a weapon that never was, a technological achievement that almost succeeded, a bridge between eras and physical evidence of humanity's ceaseless drive to build machines that fly faster, higher, and more efficiently than ever before. The Horten Ho-229 was Germany's answer to an impossible requirement, a desperate attempt to build an aircraft that could overcome the Allies' crushing numerical superiority through radical technological advantage. It failed in that mission completely, but in failing, it succeeded in something arguably more important. It proved that the future of aviation lay in unconventional thinking, radical configurations, and willingness to challenge every assumption about how aircraft should be designed. That lesson, learned by American engineers who studied the captured prototype, helped shape the aerospace technology that dominates warfare today. And that makes the Ho-229 one of the most influential aircraft never to enter operational service, a weapon that lost its war but won its argument.